Okay, let's move that off to the side. But yeah, I think the days have been a little longer, which is to be expected. There's just a lot of stuff going on, a lot of things that I'm still learning and figuring out, and a lot of questions I'm answering for people. I'll say this a little later, but like because there's so much sitting while teaching right now instead of standing, which I'm not used to, and there's also and then so like I normally this 1 hour break, like I would just be sitting in the third floor of Centennial somewhere and like grading something or doing emails, but I had to do something, like especially since I'm working so late on academic stuff. I had to, like the last hour, I'm gonna confess, I had to do something non-academic, and I'd been putting off the dishes for too long, but I was like, oh, dishes, that's a standing activity. So that's what I did, because yeah, and there were that many dishes, and yeah, well, whatever. Okay. I don't know. It's something to do, something a little different. I also played a tune on piano, which required sitting. Yeah, but like it just it's like after 2 hours of class already, this 1 hour break I have while the computer I set the laptop to process the recordings of the calculus classes, and I can't do much on the computer anyway. Just trying to break up the day a little bit, do a little something that's not academic, and then mix it into. I've got plenty of academia things to do today. After all, right after this, actually I have office hours at 1:10 or whatever, right? 1:10 to 3:10, and I have a committee meeting after. So there's gonna be enough sitting. I had to like change it up and do something that wasn't sitting. I'm sorry. I don't not that I should defend this to you. I can't even see any facial expressions. I'm just talking mainly to make sure that hopefully volume wise we're all right. I hope. I need to just remind myself to talk into this microphone loudly enough. I was actually trying to look for one of those headset thingies so I could pretend to be a pilot, and then whatever. I was looking, but everybody seems to be out of those. Surprise, surprise. 5, 4, 3, 2, and 1, and all right, here we go. Welcome back. Happy Wednesday, April 1st. April Fool's Day. Don't let anybody, I guess, trick you into anything. No, there'll be no April Fool's type jokes here. Just maybe I'll run through announcements as maybe a couple people are still joining or watching the recording later. I think as much as it's possible, I'm going to try to do announcements every day. I know it's not something I'd normally do in class every day, but I think it's just anything to help connect and make sure that all the details are there would be good. So the timing of the quizzes, I do intend for them to still all be done on Tuesdays, but I know that timing is all a little strange right now, so I don't want anything that has like too tiny of a window to turn in stuff. So that's why it was a 48-hour period. So if you have not turned in the quiz that's technically dated for yesterday, just turn it in by the end of class day today. There is also a response for today, and as is always the case by the day before an exam date, the pre-exam 2 assignment. So the response and the pre-exam 2 thing are not meant to take you a lot of time. So just kind of get those things in. Homework 7 is due at the end of the day tomorrow. Please take a look at Quiz 7 Study Guide. I just realized late yesterday that I hadn't even posted that yet. So many things. So I did post that. Though I think it's just a couple questions there that just demonstrate more Homework 7 style things, but so did the Quiz 6 Study Guide. Exam will be available tomorrow. In an ideal world, I would have already made it, but I'm still kind of scrambling and will be finished making it late today. It is, just to give a big window of time to get it done, will be due on April 6th. That said, I just want you to spend maybe an hour, or if you want to give yourself a little more time, maybe 2 hours max. I don't want you to like agonize over the exam all weekend. That's not the point. I'm trying to design an exam that, had I been printing it out for you and you take it in class, it would have been meant to be done in 55 minutes. So, spend a little extra time if you want, but just if you burn your entire weekend on that, I think that wasn't the point. You can. I can't really stop you, but I don't want you to do that. I know you've got plenty of other things you need to be doing anyway. Since tomorrow is technically an exam day, even if it is take home, that leaves us with what should we do tomorrow? And I don't want to just full on cancel class, I guess, but like what I'll do is, I haven't been recording office hours. Tomorrow I'll just leave it like as an open office hour. So if you don't feel like joining, all I'll really be doing is answering questions for people tomorrow. But I'll leave that recording for everybody, just because there are some people I know who cannot join at our live class session time. And then I'm also normally would have posted the next homework, the one that's due next week, by like a Wednesday-ish, but I'm a little behind. My priority is making the exam so that it's available for you tomorrow. And as soon as I do that, I'll also make homework number 8. Let's see. In terms of other announcements, those are the ones I think I needed to mention. If there's other questions you think of, I'll pause so that you can ask. And I guess the other thing is, I know there's going to be hiccups in the process. You all have been very kind to me so far, so I want to thank you. I know this isn't ideal, but if something comes up, if you feel like I haven't addressed something, or something's missing in Canvas, or the date of something is wrong, all of those things are possible. Just send me an email. I won't be sassy about it. You're not going to get like, oh, I already addressed this in class. Why are you asking this? Nothing like that. There's no time for that kind of thing. I will just answer your question as quickly as possible. Just send me an email. I don't mind answering something that's been answered before. I think that's just the nature of how things are. I've been getting plenty of emails, at least from my calculus class, about it. I know you're all more mature, so maybe you feel like you shouldn't ask, but no, just ask. I just seriously, like, I want, this is a strange time. So the more that I can stay connected to you and answer any questions you have, please don't be bothered about this idea of, oh, I think he already addressed it in class. No, just ask it. Just send me an email with any kind of logistics type questions related to class. You may have noticed we didn't get quite as far as I wanted to yesterday. Oh, I remembered. Sorry. One thing from an office hour visit yesterday, I wanted to just, it's good to react to how office hours went and mention something in class. Just so this is not in the notes, but I just want to say, don't assume something just because, is maybe the general point I want to make. This came up in office hours. Don't assume something just because. So let me explain what I mean by that. Like, sometimes what people do is like, they'll go, oh, I'm going to assume this additional thing because it makes my proof go easier, or I think it makes my proof go easier. But what that actually does is it changes the overall landscape of the problem by because you added something to it, right? It's like you can't just throw in an extra fact just because it's convenient to do. What I mean, and here's sort of a key situation, I have tended to see this. So there are certain times we're allowed to assume things, like when you prove when proving when you prove P implies Q, you got to assume P. That's the usual approach, like 95% of the time. So there are times you're supposed to assume things, but it's like it's built into how we prove something. So the specific example I wanted to look at is sometimes people will write as one of their first sentences, let little c belong to capital C. Now, I'm going to try to write down all of the reasons I can think of why somebody would write that sentence. So one of the reasons somebody would write that sentence is because they are trying to prove the thing that they're trying to prove starts for all whatever letter, I'll just stick with C, in capital C, and then whatever other text follows after. So if you're trying to prove a for all and the set that's there, the universe of discourse is C, that would be a reason to write the text that's in the box here, let C be in C. That would be one reason. Another reason that you would start a proof by writing the sentence, let little c belong to capital C, is you need to prove that the set C is a subset of whatever other set. I'll just call it capital E. So in that situation, if you're proving, not using, if you're proving that C is a subset of some other set, that'd be another reason you'd start by writing let little c belong to capital C. I can think of one other reason. It's sort of an accident that this is a reason, but it's just coincidence. If you were going to prove a statement that said if C is in C, then whatever, then because of the usual way of proving an if then that'd be another reason to write let or suppose or assume little c belongs to capital C. Maybe there's probably another reason that I can't think of to do it, but like it's basically these proving one of these three kinds of things. That'd be the reason you'd want to write let little c belong to capital C. So I'm trying to address something that comes up in one of the homework questions for this week. I can't think of which one, but it's easy to want to take that one set is a subset of another, but that if you know that already, then that's a fact you need to use. And sometimes you know a certain fact and you're not ready to use it right away. So just kind of go through the usual steps. Don't add any additional assumptions at the time when things are needed. Then a fact that you know can get applied later. I know that sounds a little abstract if you haven't looked at the homework, or which it's kind of late for, of course, because it's Wednesday right now and due Thursday. But in any case, I'm sorry, I'm blabbering now. Just don't add assumptions if you don't have to. Yesterday we looked at. Oh yeah, good. I have this little reminder here for myself. So yesterday, the main thing we looked at was this definition, which we didn't get as far as I wanted yesterday. It always happens with this section, and that's fine. So I just want to remind you, trying to do this from the top of my head, our main definition, which I want to dig into as much as possible today, is let R be an equivalence relation on the set capital A. So you already have to have an equivalence relation. That means that it's a binary relation on A that is all three of those other things, right? Reflexive, symmetric, transitive. And then in addition, you need to have an element from the set capital A. Those are the ingredients you need in order to create an equivalence class. So then the equivalence class, spell that. Equivalence class of A is the set. I think yesterday I didn't mention these words, the set right here, but just why not include it, is inside square brackets is the element little a. There's a subscript capital R, and this should be all of the ordered pairs A, comma, S's or whatever. I mean, S is just a placeholder variable. So where S, no, what am I doing? I need to move this. I'm trying to do this all off the top of my head. I should. Okay, so we should keep what kind of things belong to the set are little s's that belong to the set capital A, so long as this criterion is satisfied that the ordered pair AS belongs to the relation. And then the other thing about this definition is that an element B in this set, square bracket R, square bracket A inside R, is called a representative. So we kind of started playing with this yesterday. I had you write out a couple equivalence classes for a specific equivalence relation, and we're gonna try some other ones today. The note I want to make, that I wrote here sort of towards the bottom of the page as a reminder for me, is to say, note, there are situations where you can deal with more than one equivalence relation at the same time, like there's a capital R and there's a capital S. But if you're in one problem or like one proof, and this one proof only deals with one equivalence relation, then often the script R, the capital R is left, subscript R is often left out. So if it is clear which equivalence relation capital R that you're talking about, I need to move my screen. That's why my writing is terrible here. Okay. If it's clear what equivalence relation you're talking about, then as a tiny shortcut, it's a little bit less writing. Instead of writing the R as a subscript, you just leave it out. Only if it's clear. So if like the proof you have only has one equivalence relation in it. So I'm going to write down the theorem that we ended class on yesterday, and we're going to try to prove maybe all of it. We'll see. I want to at least prove some of this, and then kind of talk through what this means and what it's going to do, and try to be as informal a bit as possible, I guess. So the theorem yesterday was let R be an equivalence relation on a set, the set, doesn't matter here actually, on the set A. And then you should have little a, little b belonging to capital A. Whether little a and little b are the same element from capital A or are different elements, no comment. So this theorem works no matter what, right? So A and B, little b could be the same thing or it could be different things. The TFAE, that's an abbreviation for the following are equivalent. So part I, as yesterday, and part I. So I'm looking, basically when I look towards the camera, that's where I pulled up my notes on the other computer here. So, because I can't print, mainly because I don't have paper. Ordered pair AB belongs to R. That's true if and only if the equivalence class for A, equivalence class of A, I guess, technically, looking up at the definition. The equivalence class of A is equal to the equivalence class of B. If and only if the equivalence class of A, that set intersected with the equivalence class of B, is not equal to the empty set. Okay, so there's a theorem that we will start looking at the proof of right now. So let's just take all of this text up here as just givens. So this is, probably shouldn't be doing that, but there we go. That's the first sentence of the proof. With the following are equivalent, we haven't seen really actually many of these, but just like if you are following in the PDF from yesterday, just to outline what it is we're going to do to help the reader out, we're going to prove that condition 1 implies condition 2, then we'll prove condition 2 implies condition 3, and then we'll also prove that condition 3 implies condition 1. And we'll just kind of clearly try to separate out in each page what's going on. So the first part is to prove, we'll do the proof of part 1 implies part 2. So why don't I just scroll up slightly. Sorry to do this. So just as a note here for ourselves, right? Because it's spilling off the next page. This is one of the downsides of I don't have two whiteboards where I can point. So we're going to take ordered pair AB belongs to R and prove that implies square bracket A equals square bracket B. There. So I just copied that from over there just so that we have, we want to show this implication, right? So we want to show that arrow is an implication. We need to prove an if then. So usual story, we got to assume the first part, right? So we'll assume or suppose. You may have noticed I tend to personally prefer the word suppose. It's all personal preference. Ordered pair AB belongs to R. And then we want to show bracket A equals bracket B. Okay, I think that part's no surprise, right? For proving an if then. But now the thing to take a look at is we want to prove bracket A thing equals bracket B thing. And that bracket A thing, let's remember this equivalence class, as it's called, what kind of creature it is, because that matters. I'll give you a moment to think. But let's recall that an equivalence class, I'll scroll back up for a moment, is a set. And this time around today, I even included the language right here. I'll underline it in red, right? So we have a set. And so to prove that two sets are equal, my point is this. So we have got like this task here, this want to show. It's like, think of that's on our to-do list. But you can scratch that item off your to-do list if you show two subset things. That's just by definition what it means for two sets to be equal. So we got to prove the one set is a subset of the other set, and we also need to prove that the second set is a subset of the first set. It's just literal definition of what it means for sets to be equal. So that's what we'll do, right? So to show the first one here, so we right, you get what I mean? So the first one to show is replaced by that second one to show, but the second one to show has two separate parts, but at least it breaks it down into smaller things for us. So to show that this set is a subset of this set, we should do the usual proof method for proving one set's a subset of another. So we should pick an element of that first set there, right? The one that I just sort of square bracket underlined. I'm going to follow my notes as far as notation for what letter I see. Oh yeah, in my own notes, I picked a little x. I'm going to, you can pick any letter other than A or B right now, but I'll just stick with what I chose in my notes. I'm going to pick let x belong to bracket A. All right. I would love to be pointing to the definition written down, so I'm going to, sorry to do this, I'm going to scroll up and just steal something from up here, just so that it'll be easier, so that you can see this on screen in one place. How's that? You can get rid of that R there. Okay. So the thing is, if little x belongs to this set and this set is written down here, we should see what we get out of this. So the little s is that placeholder, right? So the facts we get are this underlined one and this underlined one. We just need to replace the placeholder s variable with our specific thing, which is x. So we end up learning that x belongs to A, and we also end up learning that ordered pair A, comma, x, again replacing the s, belongs to R. Okay, that's what we get out of this. Okay, so I should pause. I hope we're okay with that so far. I'm not seeing anybody try to unmute a microphone. Okay, and then we had this thing we supposed, ordered pair AB belongs to R, but we haven't done anything with it yet. So I'm gonna there's been a couple sentences already. So in this proof, I think it's good practice to just remind the reader, since the ordered pair AB belongs to R, and R is symmetric. I don't want to call the ordered pair symmetric. Remember, the adjective symmetric should apply to the relation. Since R is symmetric, there's a couple steps to dig through of using the for alls and all that. But the whole point is, if we just don't do too many details right now, the ordered pair AB belongs to the relation means if you swap the coordinates, the new ordered pair BA should belong to the relation as well. Okay, and then since we have the ordered pair BA belongs to the relation, we just learned that, and we have the ordered pair AX belongs to the relation. That was a couple sentences ago. Maybe I'll just box that in green, just as a reminder where I would just point on the board in class, but right there. Then we can apply transitivity. You know what? I think it's going to be a little easier to stare at this. Sorry, I shouldn't play these games too much here. If I just put this on its own line. So if you recall, the way transitivity works is if a first ordered pair's second coordinate matches the second ordered pair's first coordinate, then since this and R is transitive, this tells us that the ordered pair BX belongs to the relation as well. Now, what we should do then is, what do we conclude from here? What are we doing? Just note this definition down here. That's just for, it applies with whatever element from capital A that you have inside the square brackets. I mean, the example, the model version of this inside the definitions with a little a, but if you want as a reference, square bracket B is defined to be the set of s's or whatever placeholder variable you want, where BS ordered pair belongs to R. So take a look. The way that this is defined, the way that bracket B is defined, take a look at X. See, little x is an element of A, right? So this part is satisfied replacing the little s with a little x. We have that over here, in fact. And then the other part that we needed is this boxed green thing down there, ordered pair BX, replacing the S. So BX, ordered pair BX and R, and that was what we just got right over here. This is the most recent thing that was written as the actual part of the proof. So we have the parts needed to conclude that this ordered pair belongs to bracket B. So little x belongs to bracket B. We have a, that's 1/2, so that shows all sort of, yeah, circle that up there. We need the other direction, so I'll just do this in a new paragraph, right? To prove, to show, or to prove this set is a subset of that set. Let me move these things down a little bit for reference. In my notes I just used x. Okay, I'll just go with it. Let x belong to bracket B. Don't think the little x that I wrote is the same as the little x from the previous paragraph. That's why I started a new paragraph. Okay, and then since, good thing we still have this over here, so we get little x belongs to capital A, and ordered pair BX belongs to R. If you don't like having this paragraph have little x's, you could change up all the little x's in this paragraph to little y's. Let's also recall we had ordered pair AB belongs to the relation. This was by hypothesis. I mean, this was all, scroll up a little bit. It was way back here. It was the thing that we assumed in trying to prove this if-then in the first place. So since we have the ordered pair AB belonging to the relation, and we had just stated, it's just, I'm writing basically right underneath where you see it, we had ordered pair BX belongs to the relation by transitivity of R. We have the ordered pair AX belongs to the relation. So that's the key thing that you need. Maybe I'll box this in a new color, blue. That's the key thing that you need down there if you replace the placeholder s with x's. So we get x belong. Oh, that's blue. Oh, sorry, I was not ready for that. Okay, whatever. So it's blue, but yeah. So then x belongs to the equivalence class of A. This is a good place for me to just take a quick break and see how everybody's doing. But this should now complete the proof of assuming this. We've proved that each set is a subset of another up there. That each equivalence class is a subset of the other. Yeah, that's 1 implies 2. Let's take a look at 2 implies 3 then, if I haven't seen anybody ask anything. So, okay, so here's where we'll do a proof of part 2 implies part 3. I won't, let's see, I'll just scroll in my notes here. So what we're going to do, just because I don't have the board to we're going to prove, in other words, part 2 said equivalence class equals equivalence class, that this implies, I'll just draw the arrow, that's faster, bracket, equivalence class intersect equivalence class is not equal to the null set. Okay, so as we prove this, I think the comment I want to make, just to make sure, this is not part of the proof, but I should just comment, please ignore the thing that we assumed from part 1, right? We had assumed ordered pair AB belongs to R. So this, we don't have this right now. This was the assumption we did in proving part 1 implies part 2. So here, ignore it. It's like this paragraph we're about to write could have been the first things we wrote if we just felt like proving 2 implies 3 first. Okay, so let's do the usual thing to prove this implication here. So we're going to assume bracket A equals bracket B. Okay, this proof is actually quite a bit shorter. So we want to show that the equivalence class of A intersected with the equivalence class of B is not equal to the empty set. That there's something in there. Let's recall that the definition of this, I know it's down below, but just to make a point, I'm going to just switch the letter on you. So the S that's down at the bottom, those S's are placeholders. You could replace them with P's, so I'm just going to do that. So this equivalence class, another way to write it is P in A satisfying the condition or the criterion that ordered pair A, P belongs to the relation. Okay. Now, here's the thing. Because oh, that's an error in my notes. Oh, that's embarrassing. Okay. Because A belongs... In my notes, it says a capital R there. It shouldn't. Because little a belongs to capital A, and R is reflexive, we then get that the ordered pair A, comma A belongs to the relation. I don't have anything in my notes that clarifies why this happens, but maybe I'll just clarify down here. The thing is, we've got little a belonging to capital A, right? That where did that come from? Way back. In the setup of the theorem, it's there. Little a belongs to capital A. And then move these thingies down. And then we also had R is reflexive. Now, if you recall what R is reflexive is, it's for all A in the set, the ordered pair A belongs to R. Now, this looks confusing because there's a clash of notation. The little A's on once in this box it's not the same as that A, because it's quantified, these are placeholder variables. So I'm going to lightly cross this out and just use a new letter right now. Just maybe do like a C for all C and A. Ordered pair CC belongs to the relation. And the point is, so we know that R is reflexive because R is an equivalence relation. And if you combine, how do you use this for all? You got to have something in capital A, and we got it. So now we can conclude here that ordered pair AA belongs to R. So there's a lot kind of hiding in the argument that led us up to here. So I hope we're okay with that. Okay, so maybe that was a little too long-winded of an explanation. I got to get rid of some stuff now, I think. All right, so we have ordered pair AA belongs to R. So this tells us that A belongs to its own equivalence class. Right? If you look at the definition, maybe I shouldn't have erased it. If you look at the definition of, equivalence class was the set of all little z's in A satisfying ordered pair AZ belongs to the relation, right? So, I mean, I guess my question I'm asking is, are the two green underlined parts true if you replace the z's with little a? And they are, right? So the AZ ordered pair becomes AA ordered pair, which is why we did what we just did up there. Okay, so little a belongs to its own equivalence class. That's kind of a neat little separate factoid that we're getting for free. And since this set is equal to that set, well, we know one of the things you get when two sets are equal, it's by definition, there's actually two facts you get. You get that, one subset fact, and you get a second subset fact, but that second subset fact we don't really need right now, so I'm not going to bother writing the other subset fact. But if you have an element in one set, and then one set is a subset of another, so you get to conclude here that that same element, little a, belongs to the other set, B. That's awesome. So the whole point is, since little a belongs to this set, and little a belongs to the other set, then a belongs to the intersection of these two sets. And if there's something inside this set, by this set, I need to clarify because there's so many sets. This set underlined in a thick green. Since there's something that belongs to this set, we can conclude that this set underlined in thick green there is not the empty set, because I just showed to you that something belongs to that set. Now wait, see if we're doing all right for part 2 implies part 3. And we'll try proof of part 3 implies part 1 then, unless there's questions. I regretted erasing that earlier, so I'll just wait. So proof of 3 implies 1. So see, oh yeah, it's just hiding right up here. So we're going to prove if, I'm just copying from literally the line above, huh? If this is not the empty set, then, and I'm trying to remember part 1 myself, ordered pair AB belongs to the relation. Yeah, I guess I can look at my notes for this. Okay, so to prove this, we should suppose that this set intersected with this set is not the empty set, and we want to show that the ordered pair AB belongs to the relation. Okay, so since this set intersect that set is not empty. Now, again, we should ignore anything above the long horizontal line I just drew. So, but because this set is not empty, there exists at least one element. Maybe there's more than one, but there's at least one element in this set, because it's not the empty set. And let's just name it. So let little z belong to the intersection. So see what's going on here is I'm not trying to just throw in my own assumption. So that's the danger, I think, with the comment that I mentioned right at the beginning of class. You don't want to just throw in some assumption. Right here, I first established in earlier sentences that this is not an empty grocery bag. There's something in there. And now that that's already been established, now I'm saying, now go take something out of the bag, right? Let's just call it Z. Now, due to the definition of intersection, we get to belong to the intersection, you got to belong to both of these sets. So little z belongs to the first set, and little z belongs to the second set. So so then the ordered pair AZ belongs to the relation, and the ordered pair BZ belongs to the relation. By symmetry, let me be clear. Since R is symmetric, I want to use that grammar, making sure that symmetric applies to the relation. Since R is symmetric, ordered pair ZB belongs to the relation. Right? I just took an ordered pair that I knew belonged to R, and I swapped the two coordinates, just from the previous sentence. Since R is transitive, and ordered pair AZ is in R, and ordered pair ZB is in R, coming from the previous sentence. Good, we've got that the matchy thingy that we needed here for transitivity to be useful for us. We conclude ordered pair AB belongs to the relation, which was way back somewhere, the want to show. Here it is. I'll circle it in blue. Woo! There we go. So we've proved that 1 implies 2, without assuming 3. We applied 2 implies 3 without assuming 1. And we applied 3 implies 1 without assuming 2. So all 3 of these things all imply each other. These 3 statements are all equivalent. We have completed this monster of a proof. Let me pause. See how we're doing. Okay, so what is maybe the big point, right? So I have a bit of a fun experiment. Okay, I need to move to the correct part of my notes here. The whole point of this is the following. So I'm going to write down. Now I'm looking at my today notes, but the key thing is we get this corollary. I don't know that we've used this word corollary before. Corollary is just another word meaning theorem or proposition. So if you look at books that happen to be post Math 225, some propositions are called propositions because they're not as important. I put that in quotes. Important propositions that really matter tend to be called theorems and are often given special names. Like think about fundamental theorem of calculus, and then theorems that propositions where the proof is usually very short. Sometimes it's so short that the authors of a textbook will say, "Oh, it's so obvious, we're not even going to say anything about it." I hate when they do that, to be honest. But like if a proof is usually like extremely short and it basically uses the theorem that was just proved a moment ago, this is usually called a corollary. So I don't want to prove the core. Here I am now breaking my own rule. But I want to just kind of talk through what is going on in this corollary. And I hope you feel somewhat convinced of it based on some of the things that we have a little experiment that's going to help us out. So let me state the corollary from the notes. If R is an equivalence relation, on A, then the set A happens to be written as the union of, as you go through each little element, each element little a and capital A, the equivalence classes. So I know due to some interest of time earlier in the semester, we never really got to talk carefully about this notation. So what the heck do I mean by this? I mean the same general principle as when you see sigma notation. So when you see like I equals 1 to 10 of I squared, there's 1 squared plus 2 squared plus 3 squared. Same idea, where this is 1 squared plus 2 squared plus 3 squared, all the way up to plus 10 squared. Same general idea. It's just now over here, it's with union symbols. So maybe I'll just make a brief example. Let's just say you had a set A that had just the numbers 1, 2, 3, 4. Then under that situation, this thingy it's meant to be plug in 1 for A, plug in 2 for A, plug in 3 for A, plug in 4 for A, but the symbol in between is not a plus sign like you normally use for sigma notation. It is instead a union symbol. So it's like, sigma notation has its pros and cons, and sometimes it's the most useful way to try to talk about something in a precise manner. Same thing with this big cup symbol. Oh, BT dubs, that is, by the way, how you get this in LaTeX, if you're just curious. That's kind of fun, right? Like there was cup, now this big cup. I'm trying here. All right. All right, so the whole point is, so what is this statement over here really trying to say? Let's say you have an equivalence relation. That's the only way this writing those brackets makes any sense. Then the whole point is your set that you have is just union together all of the possible equivalence classes that you could possibly make, right? Every time you have an element little a in your set capital A, that little a, put brackets around it, meaning make its equivalence class. What are the things it's related to using yesterday's language? Look at each of those sets, union all those sets together. If you do that, you get all of the set A. And this has actually a really important implication what I'd like to do, I know this is going to seem a little strange, but I'd like to look at a new equivalence class, one that we did not look at yesterday. Let capital M be the set of all students in Math 225. I have to confess, I just made mostly a copy of my notes from last time. So if you're looking at my notes, there's actually another little technical error there. I claim in my notes that the cardinality of M is 28. That was true last semester. This semester, the cardinality, I believe, is 23. I'm trying to do this off the top of my head. I'd like to introduce to you a binary relation on M. So this is the set of ordered pairs, little m comma little n, belonging to M Cartesian M, which satisfy this additional criterion that M was born in the same month as N. Now, I don't want to do a formal proof right now, but I just want you to think about this, that let's just note R is an equivalence relation on the set capital M. So I've switched from capital A. I know we're used to that so often, but it's got to change this up too. M, I guess, for math, right? First of all, without actually just proving it, let's just think if R is an equivalence relation, by definition, it has to be reflexive, symmetric, and transitive. So reflexive, meaning if you take an arbitrary student in our class, was that student born in the same month as themselves? Well, yeah, right? Each person is born in the same month as themselves, so that should cover reflexive. The symmetric part, so pick two arbitrary students. Is the following implication true? If student 1 was born in the same month as student 2, then student 2 is born in the same month as student 1. Yeah, that works. I mean, the first part of that implication could be false. If you pick the two arbitrary students that you pick, maybe they weren't born in the same month. Well, then the if part of the implication is false, which makes the implication itself true. But the causality is there. If person A and if person little m and person little n are born in the same month, then of course person n and person little n and person little m are born in the same month. Transitivity also follows, right? If one person's born in the same month as another, and that second person's born in the same month as the third person, then the first person's born in the same month as the third person. So at least informally, without writing out all the let whatever be arbitrary in capital M, I hope you're seeing that this should be an equivalence relation. And now it's time for the experiment. So to try to really make sense of what's going on, I bet you're all sitting like me, but we're going to run a little experiment. I know this sounds silly. I'm going to ask you to stand at the appropriate time. Now, you might be connected using headphones to some electronic devices, so please be careful as you stand so that you don't run into any, you don't make a electronic device fall off your desk or something like this. But can I have everybody who is born in the month of January please stand? Everybody look around the classroom and then you can sit. Thank you. Everybody who's born in February, please stand. Then you can sit. Nobody's camera's on except mine, so I'm just trusting you're doing this. It's good. Little juice is flowing. Everybody born in March. Okay, thank you. And then everybody born in April can stand and sit down. And then everybody born in May can stand and sit. And then everybody born in June, stand, sit. I should have just done hand raising. Everybody born in July can stand. That's me. All right. Okay. Summer babies. All right. And then sit. Everybody born in August, stand and have a seat. Everybody born in, what's the next? 8, 9, 9, 9. September. Oh my goodness. Stand. And sit. Everybody born in October. Have your moment to shine. And then sit. And then everybody born in November, stand, sit. And everybody born in December can stand and then sit. I know this experiment was a little silly with only 23 people in the class. It is let's just assume everybody did it, or at least just play the video in your head. If we're all, imagine in Centennial 3213, I think was our classroom. You can imagine that at some point in time, nobody was standing because we just maybe had nobody born in the month of, I'm not even going to guess because I'll probably be wrong. But that could very well happen with only 23 people. Certainly wouldn't happen if there's like 200 people, right? I mean, it could. Here's the thing. The main thing I want to point out is that everybody got to stand once, right? Everybody should, if we all did this, everyone stood once. And by once, I mean like once and only once, not twice. You can't be born in both April and June, for instance. Also, nobody stood a zero number of times. Like everybody actually stood. And so that the idea here is, if I go back to what's in the box over here, and I'll just copy paste this down here so that we can talk about it. Here, I just need to replace the capital A with M. So M was the set of all students. Oh, wait, I should not have stood myself. Okay, whatever. Anyway, the whole point is, if you take here the set of all of you, the students, then we should go through each student in the class, like literally scan the room one at a time, and like so I should like look in the left corner of the room and say, can you just identify your set of people, the same people you stood with? Because that's what one of those would be. But just union all these together, and you get, in terms of sets, in the end, when you take all these unions, since everybody stood at least once, you get all the people, you end up getting the same set. You get the set of all the students who are in the class. So I know, as silly of an experiment as this was, it helps to at least a little bit clarify what's going on, is that when you union together all the possible equivalence classes you can find, you get the entire set, capital M here, capital A in general. And then really the only last thing I want to do is end on this definition. I don't want you to stress about this definition all that much. It's a complicated one. I'm not going to really quiz you on it heavily, but it's one that, because it is so complicated, it's important to have seen this more than once, in the sense of like math classes past this. You got to just see it once here so that you're used to it for the next time you see it. So let S be a set, any set. A partition of S is a collection of subsets. Let me label them as A with a tiny little subscript I, as little I belongs to a set called capital I. Of S with the properties. So there are three properties here. I, and I. I don't know, I went with Roman numerals, but we'll just stick with it here. So each of the sets should not be the empty set. So this should happen for all little I and capital I. So none of these A sub i's are empty. Sorry, I think I just bumped my microphone. I hope that was not too loud. If I is not equal to J, then A sub I intersected with A sub J should equal the empty set. And then if you took all of these A sub i's all together and union them for little I running through capital I, you should get the entire set S. This is what's known as a partition. Again, I don't want you to stress so much about this. What I want to do actually is to try to just give you an intuitive idea using a picture that if you have a set S, now this applies to any set, but let's say that the set, especially this last condition, let's just go with I, just to connect it to the standing experiment we did, is 1, 2, all the way up to 12. I picked 12 because there's 12 calendar months. So then this S equals union A sub I not equals, I member of capital I, because over here I only has 12 elements, and we could write this out. It's A1, union A2, union A3, union A4, union, and so on, all the way up to A sub 12. And the whole point is, if the set S can be broken down into these pieces, it's like that subset A1 might be one of these, just in terms of Venn diagram style picture, might be that subset of S, and maybe A2 is over here. A3 might be this, but there's no overlap. None of these, and that's what part 2 is about. If you are dealing with different subscripts, so I and J are different subscripts, so I not equal to J, then the intersection of the two sets needs to be the empty set. A4, A5, A6, A7, A8, A9, A10, A11, A12. That, it's just a cartoon to say, like, let's say that the S here is actually the set M we had earlier. So it'd be more like what's this Venn diagram? It's like if I could get you all physically in the classroom to, like, all the people who were born in January all clumped together in the same part of the room, and then just like put a like a hula hoop around you all and say, okay, you're a certain subset of the whole class of M, and that equivalence class, since nobody belongs to, remember, nobody belonged to 2 equivalence classes because nobody was born in both May and March or something like that. So what happens is when you have an equivalence relation, the equivalence classes, like in this example, the 12 equivalence classes corresponding to the 12 months, those end up forming a partition. And so these 3 parts, 1, 2, 3, that are labeled here, they actually go back and are addressed to be true because of the 3 parts of the large theorem that we proved at the beginning. Moral of the story: if you have an equivalence relation, think about the example with the same birthdays one, then the fact that nobody stood twice is what corresponds to this part 2. The part that everybody got to stand at least once is the part that's telling us when you union together all of the equivalence classes, you got the set S, or in our case capital M, of the set of all the students in the class. And the part 1, sorry, I've avoided this so far, you're saying, like, hey, wait a second, what if there was a month, an equivalence class that was empty because nobody was born in a certain month in our class? Well, we should just cut out that month here, so maybe we have to do the experiment of a much, much bigger classroom where we would be guaranteed to have somebody born in every month or something like that. Okay, I know this last thing was sort of the strange topic. Don't stress too much about this definition of partition. It doesn't come up all that often for us. In fact, it may never for us, but I needed to just have you see this thingy once. I think the main thing maybe about today's class is this theorem that we proved took quite a long time, and I think it was kind of good to just see some of the parts of that. I think I'm done. So just in terms of announcements, just please, let me scroll to the top because they're up there. Tomorrow, if it's okay with y'all, we'll just do a kind of an office hour drop by if you want to and ask your questions. But since it is during the class time, just so that everybody has it, I don't want to record office hours in general, but this one I will. Thursdays 11 a.m. to noon class time. And then by the end of the day, I will have exam 2 posted. It should be available to you starting at midnight. So I think that's everything. Maybe I'll see you in office hours.